All right, let's get this lesson on the road for Algebra 2. Another strange way to have a lesson, but we're going to have to make it work because I am in quarantine. So, welcome to this lesson, my 7 students. Hopefully you are enjoying this really strange day at school. Hopefully this video will help you with these particular sections. There's going to be 4 of these videos throughout the next week because I won't be back this whole week. So what's going to be happening is you're going to have a video, and throughout the video there's going to be questions popping up that you'll have to answer, just so that I know that you're paying attention to the video. I know that probably sounds annoying and frustrating, but it's a way to make sure that you're still in check in regards to the stuff that we're talking about. We are talking about correlation and modeling linear data. So correlation, modeling linear data, we're going to talk about how different data points are related to each other in a particular graph and how we use those trends to draw different conclusions about the future, make different predictions. This is all basically statistics stuff, and you're most likely going to be taking a statistics class when you get to college. So this is kind of an introductory thing for statistics. Make sure you have your notes out and they are turned to the modeling linear data page. So that would be for section 2.4. So make sure that you have your notes open before we start this video. Alright? Okay, let's start. Alright, so this is the first section of your notes. So we started this on Wednesday of last week, but we weren't actually able to finish it because we were going over quizzes and stuff. So I was just going to go over it again. So one way we can represent a particular set of data is using a thing called a scatter plot. You've probably heard the term scatter plot before, but a scatter plot just maps all these points of data, and then we can use it to determine different trends in our data. So this is comparing training miles to a 10K runtime, so 10,000 mile runtime to the nearest minute. So what we are doing is we're going to plot the points from the table onto the graph, and we are going to figure out what we can do with the data once we do that. So I'm going to whip my pen out here. So training miles. So we're going to start off with training miles is on the x-axis, because remember, this is similar to a t-chart. X and Y. So X and Y, this is our t-chart. You have your training miles 100 to 600, so we're going to use the 6 different points on the x-axis and compare it to 10K runtime. So we're going to map 100 to 70 first of all. Alright, and then 200 to 67. So that's right about here. With these, you're going to have to kind of eyeball it. We're going to go over how to use a program in order to figure out these different things. You have a program similar to what I'm going to use on Chromebook, so we're going to use that as well. Training miles. So we're going to map x 300 53. Okay? So scatter plot, we're just plotting the different points to compare data. We're comparing training miles to 10K runtime. 400 55 55. So there we go. And then 500 to 44. So right about there. And then 600 to 47. Alright, so we have all this data plotted now, and when you look at it, you can kind of know if it's a trend within the training miles and the 10K runtime. So our miles, the amount of miles that we run, seems to bring the 10K runtime that we have down by a certain number of minutes. So that is what we would call a correlation. So there's a negative correlation because it's going down left to right. We're going to talk more about this in a minute. There's a negative correlation between how much we train and the 10K runtime that we have. So in order to better illustrate this, I'm going to draw a trend line. And what a trend line does is a trend line takes the data that we have and kind of creates a visual trend of that data in order to make a prediction. So our trend line if I look at this data, our trend line could most definitely be something like this. All right. So a trend line is just used to kind of create a general average of our data. So general average of our data to make conclusions with our graph. All right. So the question is asking us how many miles practice to run the race in 30 minutes. So it's asking us how many miles will we have to practice to run the race in 30 minutes. And based on the trend line I drew, it looks like it will be about 650 miles. All right. So that's why we use trend lines in order so we can make predictions based on the set of data that we have. So this data that we already started with, we can use on a scatter plot to make conclusions about future data. All right? So that is why we use scatter plots, okay? All right, with scatter plots, we have a thing called correlation. Remember, correlation, going back to this, talks about how basically the trend within the data between the x-axis and the y-axis. It is a relationship between our two variables, x and y. All right, so our x here is training miles, our y is 10K runtime, and we're comparing the relationship between our training miles to our 10K runtime. All right, so that is what correlation is referring to. There's two types of correlation. There's positive correlation and there's negative correlation. So positive correlation would be the opposite of this graph. This graph shows negative correlation. And why does it show negative correlation? So a graph showing negative correlation will have a trend that's going down from left to right. So our data set will trend downwards going left to right. So basically, negative correlation, we start high on the y-axis and go lower on it as we go towards the right. So there's a negative correlation between our 10K runtime and how many miles we train. The more miles we train, the lower our 10K runtime is. However, a positive correlation. So if I were to draw this out, this right here is a negative correlation. This right here is a positive correlation. All right? The reason why that is because as x increases, y increases. That's a positive correlation. As x increases on this graph here, as x increases on this graph, y decreases, and that's why it's a negative correlation. Okay? So that's the two different things. And then this also has a positive correlation, and this graph has a negative correlation as well. So if you want to really get a good idea of what correlation we're dealing with, you can just look from left to right and say, hey, is the trend line on this graph going up or is it going down? If it's going up left to right, it's positive correlation. If it's going down left to right, it's negative correlation. Okay? So, considering the strength of a correlation is important. So, if you have data that is very close to the trend line, for example, this data here is very, very close to the trend line. This is what we would call strong positive correlation. Okay? Strong positive correlation means that our data is very representative of the trend that we are seeing. So our trend line pretty much matches our set of data, which means it's strong. Same with this graph, except it's strong negative correlation because it's going down left to right, and our data set is very representative of the trend that we are seeing. Okay? So that's strong negative. This, however, would not be as strong. All right? So this is not as strong of a correlation that we are seeing. All right? Just want to make sure you're seeing it. All right. So this is a weak positive correlation, I'd say. A weak positive correlation because our data does not match up as much with the trend line. It's out there a little bit, okay? It's a little bit distant from the trend line. The closer it matches up to your trend line, the data, the stronger your correlation is, okay? So stronger correlation. That's how this works. However, this over here is weak, negative correlation. Your trend line's going down, left to right, and the data is a little bit outside the trend line, okay? Hopefully that makes sense. This is what we're talking about with positive and negative correlation. All right. Sometimes, if we're dealing with correlation, we like to represent correlation with a number. It just gives us an idea of what we're working with. And that number is called the correlation coefficient. The variable we assign to the correlation coefficient is R. So the correlation coefficient, or R, this is in your notes, numerically represents the strength of positive and negative correlations, okay? So it numerically represents it. R, or the correlation coefficient, represents, another way to put it, is it represents the degree to which two variables are related. So, an important key thing to note about the correlation coefficient is that it never goes below -1, and it never goes higher than +1. You're probably asking, why is that? Well, if R equals 1, for this example, that means you have very strong positive correlation. That means you have perfectly strong, like perfect positive correlation. So remember, this graph is the same thing that we saw back here. This strong positive correlation. R equals 1 when all the data points are matched with the trend line. Okay? So that's when R equals 1. We'll talk about R squared in just a minute. But R equals 1 represents strong positive correlation. And then R equals -1 on the opposite side of things represents strong negative correlation. So all the data points are matching the trend line, except it's going in the negative direction. So as X increases, Y decreases. However, when you have weaker correlation, you get your decimals, or parts of a whole, that represent that correlation. It just represents the spread or strength of your data. So 0.7 has less strength in its correlation. It's still positive correlation, but the strength isn't there. All right? Whereas in this graph, you have -0.6. -0.6 represents weaker negative correlation, okay? So whenever you're in the negatives for R, it's a negative correlation. Whenever you're in the positives, it's positive correlation. But as you get closer to 0, I can't find my pointer. As you get closer to 0, the correlation gets a lot weaker, okay? All right, so that is the correlation coefficient. All right, so we went over this. It numerically represents the degree to which the two variables are related. The closer the absolute value R is to 1, the stronger the correlation between the variables. That means that the closer you are to either 1 or -1, you have a stronger correlation. If R equals 1 or R equals -1, all the data points will be on a line with positive or negative slope. We talked about that as well. If R is near 0, the points appear to be randomly scattered. If R equals 0, that means we have absolutely no correlation. That is possible on a graph, that we have no correlation. So R equals 0 means no correlation. All right? All right, another thing that I haven't mentioned is that outliers. Outliers are points that do not seem to fit the trend of the scatter plot. So if you see a point that's way out there, so let's say I had one of these points and it was way up here, this would most definitely be an outlier because it doesn't fit the trend of the scatter plot. So outliers are points that do not seem to fit the trend of the scatter plot. And in statistics, you will very often get outliers. All right, so coefficient of determination, that's just R squared. So you're squaring whatever R is. All right, so it explains how much variation in the dependent variable is, how much variation in the dependent variable is explained by the independent variable. So in order to explain this, take a look back at our t-chart. In a given function, y depends on what x is, right? So if I have the function y equals x minus 1, whatever x is, so say x is 1, y would be equal to 0. All right? So y depends on x. So that means y would be our dependent variable and x would be our independent variable. So r squared explains how much variation in y is explained by x. Okay? So take a look at our x-axis and our y-axis here, okay? If you have r equals 1, that means all of your variation in y is explained by x. So whatever x is, y fits the exact same trend that it would normally do that. There is not much, the variation is pretty much not even there. Or it's fully explained by x, is what it's saying there. Same with this one, except it's negative. Notice here, r squared is still the same, because what happens when you square a negative number? Two negatives make a positive, so it's still fully explained by the independent variable, because your y values still match up with your trend. All right? Now, the real difference that comes is when you have weaker correlation than 1 or -1. So in these examples, okay? So notice how, based on our trend line, how our y values are a lot different than our normal trend line. This is where we would have a certain part of our dependent variable explained. So our y values, our different y values, are explained differently than what x would predict. So that's why the coefficient of determination says that only 49% of our variation in y is explained by x. Same with this one, except it's a little weaker. 36% of our variation in y is explained by x, because x would predict that this trend line here would be our y values. But our y values are sitting a little bit outside of our y values, okay? Our typical y values. So that's why we say 36% of our dependent variable, or x, or our y, is explained by x. All right? That was a lot, but remember, you always have this video to come back to if you have any questions regarding correlation. All right? All right, so this is just another example of a graph, a scatter plot. So if I were to draw a trend line, this is a more applicable situation. So we're comparing our independent variable, which will be temperature, to our dependent variable, which is the amount of sales. So remember, our independent variable is x, and our dependent variable is y. So we're comparing the temperature to the sale of ice cream. Okay? And what do you notice about our ice cream sales? Let me draw a trend line. So what you notice about our data is that as the temperature increases, the sales increases as well. So that means we have positive correlation. I'm not going to write it all out, but positive correlation. So positive correlation means that as x increases, y increases, right? So as temperature increases, ice cream sales increase. All right? Now, I would say that this is strong positive correlation, despite the fact that it's spread a little bit off the trend line I drew, okay? I would say the R value, if I were to just eyeball it, is about 0.85. So 0.85, all right? So that kind of gives you an idea of what we're talking about with the R. So there's a little bit of spread, but not a ton of spread. If all of these points were on my trend line, it would be R equals 1. But it's not. There's a little bit of spread. I would still say 0.85 for R is strong positive correlation. And some of these, when you do some of these on your homework, you're actually going to have to eyeball it as well. So I'm not going to be a huge stickler to if you don't get it exactly what the book says, because sometimes the book's wrong too. So you're going to have to do some of this on your homework though. All right, now we're going to get into the technology side of things. So we're going to use technology to create a scatter plot of the data in the table. This is where Microsoft Excel, in your situation on Chromebooks, you'd be using Google Sheets, but we're going to use technology to create a scatter plot of the data in the table. So I'm going to pull up Microsoft Excel. For you guys, it's going to be Google Sheets. So when you're using a spreadsheet, this is a spreadsheet, Google Sheets also uses spreadsheets, you would label your different variables. So remember, homework average is my X. It's my X value. So let's mark that real quick. Compared to test scores, which is Y. Okay? So let's graph one of these. Let me pull up Excel again. All right, I'm going to label this homework average. And that'll represent my X value as homework average, which it is in the actual plot. So homework average compared to test score. So we're examining the relationship between homework averages and test scores. So let me enter in all this data, 100, 96. Spreadsheets make it way easier. If you had to do this on your own in real life, it'd be a lot harder. So hopefully you're thankful for your computer today. 68. I don't know where I got 68 from. I need to correct that. 88 and 78. Okay, 88, 78. And then comparing that to our test scores of 99, 91, 56, 80, 89, 78, 90, 75. All right, so I have all of my data points, my X's and Y's filled in. So now I'm going to select those data points, and then I'm going to create a chart. And it recommended to me a scatter plot just like that. And bingo, we have a scatter plot. Let's enlarge it so you can see it better. Okay, so this chart is comparing homework average to test score, okay? Homework average to test score. The axes aren't labeled. I'm not sure why they didn't label, but right here is your homework average, your x-axis, compared to your test score. All right. So I have the option of adding a trend line. You don't have this on Google Sheets, so you don't have to worry about it. But this will demonstrate our trend line here. I'm not going to look for a coefficient of determination, but if you notice, what kind of correlation do we have? We have a positive correlation. So homework average is a good indicator of test score based on this graph. If you spend time in your homework, you'll do well in tests. That's what this graph is really saying, and that's the conclusion we can draw from it. All right. So we can use these also to make predictions, and you're going to be doing that a little bit on your homework today. Okay. So your homework assignment is on Google Classroom. Make sure you take a look at it. And again, I'm always available if you have any questions regarding your homework. All right. All right. I wish you luck, and hopefully I can come back soon to help you guys when you need it.